what we have been examining up to now was the second order circuits. So we found the mathematical model of it, and then this mathematical model was the state equations, differential equations. In here we examined how we solve the state equations, and now we will be examining this chapter, this frame now. There is a relation between the characteristic root and the stability. So let's examine this now. Here we are. So this is now that is the characteristic equation for a parallel connected second order circuit. Characteristic equation becomes this. If you find the roots of those of this characteristic equation, you end up with this. So if you write it in different format, it is like that. So if there is a complex root, the complex conjugate of this root is also another root. So this real part of this root is called Neper frequency. The inside of it is called resonance frequency. So if the roots are real, that means alpha square is bigger than omega 0. So if this is bigger than if this is positive, so then S1 and S2 becomes real. If this is negative inside, then it's going to be a complex conjugate root. If this is equal to 0, it's going to be multiple roots. So there are three root types, and how we are going to observe these root types, we just said that. Once you found all these characteristic roots, your homogeneous solution is going to be this. In order to determine the stability of a circuit, we say if these quantities that we are dealing with, in this case is the capacitor voltage, inductor's current, and this is the homogeneous solution plus the particular solution, gives you the general solution. So this becomes general. So what happens is this: if the particular solution goes to infinity, what does this mean? Particular solution is a solution in the form of independent source. So independent source could be a DC source or AC source. If it is DC source, it is a constant. So that means it doesn't go to infinity, isn't it? When t increases, this function does not increase, it stays as it is. So that means this part of this function does not go to infinity. What about the AC type source is included in our circuit? When it is AC type, it is going to be something like that. This cosine function values is in between plus minus 1, we know that. So this function values are going to be in this interval, isn't it? So this is a definite number. Since if it is a definite number, so we can say that if the independent source in our circuit is an AC source, then particular solution is going to be a finite function. If it is finite function, that means from the particular solution, we do not have an infinite Gauss function. What does this mean? Forget the particular solution. So how I am going to check whether this function, the general solution, goes to infinity or goes to a real number? I've got to examine the homogeneous solution. If you look at the homogeneous solution, these coefficients are the constants. So I've got to look at these characteristic roots. So question is, how can I say whether a circuit is stable or not by looking at the characteristic roots? So that's the case now. So in this case, we are going to examine three alternatives. One of them is real roots. If the roots are negative, so both of them smaller than 0, so my function homogeneous solution is going to be in this format. So these are the exponentially decreasing functions. I could have done it in a better way anyway. So these are exponentially decreasing functions. It could be, depending on alpha value, it's going to be something like that. That's TV. If one of them, let's say just one of them, one of the real root is positive, then it's going to be exponentially increasing function. So that is to be something like that. Oh, no, sorry, come back to it. V, T. Exponentially, if initial condition is 0, so it's going to be something like that. Depending the alpha value, it's going to be like that. So in this case, it is unstable. That means this function here, VC or IC, goes to infinity when the t increases. So it is unstable. If the t increases, my quantity, capacitor voltage or inductor current goes to 0, goes to a finite number. If it is a finite function, that it is stable. So let's use another color for the complex roots. So in this case, my homogeneous solution is going to be in this format. If the complex characteristic root real part is negative, so my homogeneous solution is going to be in this format. These are exponentially decreasing functions multiplied with the cosine circuit. It's going to be something like that. T, V. So it's going to go to 0 because these are exponentially decreasing function. So this is stable, isn't it? When t goes infinity, V stays as constant or 0, so stable. If the complex characteristic root real part is positive, so my homogeneous solution is going to be in this format. So this is exponentially increasing function multiplied with a cosine function. So if we draw this function, it's going to be something like that. That's unstable. So the last one is when the characteristic roots are multiple roots. So our homogeneous solution is going to be in this form. If these multiple roots are real and negative, then my homogeneous solution is going to be like that. And we've got this. So this goes to 0, I know that. So we've got to examine this one. So t times e to the minus at is going to be, if I put this one underneath, so it's going to be like that. When t goes infinity, this goes infinity, this goes infinity, so undefined. So if you use the Hospital rules, so derivative of this gives you 1, derivative of this gives you alpha times e to the power alpha t. So when t goes infinity, this term goes to 0. Result, this term goes to 0, and this term also goes to 0 if the multiple roots are negative roots. So that means stable. If it is other way around, that means multiple roots are positive, so our function is going to be in this form. So this is exponentially increasing. I am not going to check this, since this is increasing with time. So that means this function goes to infinity, so that's unstable. So let's put all these results together. So when we are talking about real roots, real number roots, and the complex roots. So I am going to draw here a number plane, includes complex numbers and the real numbers. That and that. That's the real axis, real. And this is imaginary axis. So J something. So if we are talking about this case, that means characteristic rules are real and negative. So that means you are somewhere here. Let me change my color now. So we are here, somewhere here, for this case. So that means this case. If you look at this stability here now, if the characteristic roots are complex and real part of this complex number is negative, that's the case, isn't it? That's the case. So that means this case is you are somewhere here, either here or either here. Why we said so? Because this is the complex number area. If you say the complex number real part is negative, that means you are on this area, this part of the plane. So it could be maybe minus 3 plus 5j. So 5 is going to be here, minus 3 is going to be here, so that point is somewhere here. If it is minus 3 minus 5j, complex number once again, it's going to be here. So complex conjugate two numbers. So what is the property of this complex number is that real part of this complex number is negative, definitely. If it is so, we said it is stable. So if we put it together, so in order to have a stable circuit, my characteristic root should be on the left hand side. So it is true for the multiple roots as well. In here we said if the multiple roots are negative and real, so that means you are on this axis and this part of the axis. So that means, now conclusion, this complex number plane, if the characteristic root is the left hand side of the plane, it is stable. What about the right hand side? So use the blue one. Right hand side, we said if the real roots and roots are positive, so it is going to be unstable. So real roots with and positive, that means your roots on this axis and on this axis and this part of it, not this part, because it is positive. For example, plus 2, plus 3, plus 4. If it is this case, so we said it is unstable. So if you look at the complex roots, it says real part of the complex number is positive. So all the numbers here, right hand side of the complex number plane, in here the real part of the complex number is going to be positive. For example, that's going to be plus 3, and it could be plus 3j, isn't it? So this is the complex number. The symmetric of it is going to be plus 3 minus 3j. So we said if the characteristic root's real part is positive, this case, that means you are on the right hand side of this complex number plane, then it is unstable. So it is true for the multiple roots as well, because for multiple roots bigger than 0, it is unstable. So it is on the right hand side. Conclusion is that if the characteristic root is on the left hand side of the complex number plane, circuit is stable. If it is right hand side of the complex number system, then it is unstable. Circuit is unstable. So that's the end of this video.